Okay, for stagnation state, there are two stagnation state. I think not most, all of you already familiar with this H enthalpy and S entropy diagram in thermodynamics. Okay, so this straight line, which is the entropy is constant. Okay, when the entropy is constant, we call it as isentropic process. Okay, so in a very simple definition, isentropic meaning that it is an ideal situation. Okay, what is ideal situation? We consider no friction between the fluid inside the control volume, so it is an ideal situation. But however, for the actual stagnation state, actual process, there are friction. For example, there are friction in between fluid and the piping system, for example. So this friction will cause the pressure is lower than pressure for the isentropic stagnation state. As you can see, the pressure is lower than isentropic stagnation pressure, since entropy increase. Okay, entropy increase during the actual stagnation process as a result of fluid friction. Okay, due to the fluid friction, the entropy also increase. Okay, and then the entropy increase, the pressure for the actual is lower than pressure for the isentropic stagnation state. Okay, so for the fluid, when the fluid is approximately as an ideal gas with constant specific heat, okay, so Cp T0 equal to Cpt plus V squared over 2. Okay, so basically this equation comes from comes from stagnation enthalpy. Okay, stagnation enthalpy H naught equal to H plus V squared over 2. Okay, so from previous slide. So in thermodynamics, you learn about enthalpy equal to H equal to Cpt. Okay, so H equal to Cpt0 equal to Cpt plus V2 squared over 2, or stagnation temperature equal to T plus V squared over 2 Cp. Okay, so the total or the stagnation temperature, it is summation of the static temperature. Okay, T is static temperature, and also dynamic temperature. V2 squared is known as dynamic temperature. Okay, so this dynamic temperature, okay, so V squared over 2 Cp is dynamic temperature. So when we have fluid, and then we completely stop the fluid, or the temperature is increased due to this dynamic temperature. Okay, so that is how we obtain the stagnation temperature. Okay, so stagnation temperature will slightly increase due to this dynamic temperature. Okay, okay, so that was for the stagnation temperature. Now for the stagnation pressure, so same definition. Stagnation means that the pressure of fluid attains when brought to rest isentropically. So this is recall your thermodynamics, P0 over P equal to T0 over T K, which is specific ratio, K over K minus 1. Okay, so this is very important equation. And then we have another one, which is we replace with a density. Okay, so density at adiabatic stagnation density equal to rho 0 over rho equal to 1 over K minus 1. Okay, so this is very important equation in this chapter. Okay, I think all of you are definitely familiar with this equation of state for the pressure, for the temperature, and also for the density. Okay, so this is energy balance for steady flow device. But most of our cases we considered adiabatic, which is no heat transfer and then no works in our analysis. Okay, you may try to answer, try to solve this example 12.1 in order to get familiar with equation of a state for the stagnation, how to find the stagnation temperature, for example, how to find the stagnation pressure, okay, when you have the static pressure. Okay, so you may try to solve this example. Okay, so basically in our chapter, in our syllabus, our interests are more about how to analyze, for example, you have a nozzle, converging, diverging nozzle, and then how we analyze based on compressible, and then the analysis is based on the Mach number. Okay, so in I think Mach number, basically it is a ratio of this is Mach number. So Mach number is basically ratio of fluid velocity to the speed of sound. Okay, and then speed of sound, it is depending on this square root of K, R, which is gas constant, and then K is ratio of specific heat constant, and then T is temperature in Kelvin. Okay, so you have to remember that in order to solve for equation of state, temperature must be in Kelvin. Okay, because all the constant, for example gas constant, is the unit is in Kelvin. Okay, okay, so there is Mach for the Mach number. Mach number equal to V over C, which is ratio of fluid velocity over what's called the speed of sound. Okay, and then during fluid flow through many devices such as nozzles, diffuser, and turbine blade passage, flow quantities vary primarily in the flow direction only, and the flow can be approximated as one-dimensional isentropic flow with good accuracy. So now for this analysis, we just consider one-dimensional and then isentropic. So as I explained before, isentropics mean that we consider the flow is an ideal flow. No such friction is considered in our analysis. Okay, so since we have, let's say we have nozzle. Okay, nozzle. Okay, nozzle. State 1 and state 2. Okay, so at based on this nozzle, there are a variation of area. Okay, so as you can see, there are variation of area from bigger area to a smaller area. Okay, and then in this study, based on the Mach number equation, we need to come up with how to say that, the relationship, what happened when the area is changing from large area to the smaller area, what happened to the pressure, for example, what happened to the temperature, what happened to the velocity. Okay, so this is will be learned in this chapter. Okay, in order to come up with that such relationship, let's try to answer this simple example. Okay, so you have carbon dioxide flows steadily through a varying cross-sectional area duct such as nozzle shown in this figure. At mass flow rate, okay, so given m dot equal to 3 kilogram per second, the carbon dioxide enters the duct at pressure of 140. So static pressure is 1400 kilopascal and 200 degrees C degrees C Celsius, or equal to 47 degree Kelvin, with a low velocity. Okay, low velocity, V is very low. Okay, so this is important because in order to find, for example, the static in order to find the temperature, okay, the stagnation temperature, when the very low, mean that the stagnation temperature is considered only or it is equal to static temperature. Okay, and it expand in nozzle to a pressure of 200 kilo Pascal. Okay, so from 1400 kilopascal, it is expand up to 200 kilopascal. The ducting is designed so that the flow can be approximated as isentropic. Okay, so isentropic is very important. So no such friction is considered. Determine the density, find rho, velocity, area, and Mach number at each location along the duct, okay, that correspond to a pressure drop. Pressure drop delta P equal to 200 kilo Pascal. Yes, kilo Pascal. Okay, so now you have this nozzle. Okay, so consider as nozzle with m dot equal to 3 kilogram per second. Okay, so solution. First thing first, when we want to solve for this compressible flow, we need to identify the stagnation properties. Okay, so first step, we need to identify the stagnation properties. Okay, so mean that T0, P0, for example, or rho 0. Okay, so now based on all the given information, we first need to find the, for example, we need to find the temperature. Okay, so how to find the temperature, the stagnation temperature? So from previous note, previous slide, stagnation temperature equal to T naught, the summation of static temperature plus with dynamic temperature, which is V2 squared over 2C 2Cp. Okay. However, in this example, velocity is considered as very low. Okay, so I mean that no such velocity for is no such will dynamic temperature is that can be considered in this example. So I mean that for stagnation temperature, it is equal to T1, which is equal to 473 Kelvin. Okay, and then the same goes for P0. Okay, stagnation pressure. For the P0, using the previous equation, this equation P0 over P equal T0 over T K minus over K minus 1. Okay, so based on that equation, we P0 over P equal to T0 over T K over K minus 1. Since T0 equal to T, and then P0 will also equal to P1, which is equal to 1400 kilopascal. And then the solution, the question asks you to find all the properties, okay, all the properties, density, velocity, area, and Mach number along the duct that correspond to a pressure drop of 200 kilopascal. Okay, so mean that from 1400, now we find 1200 kilopascal. Okay, so now for so for 1200 kilopascal, we can determine the temperature. Okay, so we can determine the temperature at 1200 kilopascal. Okay, so now to find that temperature, we use the same equation. Since we have T0, we have P0, and then we have P. Now we can determine the temperature. Okay, so now T0 over T equal to P0 over P K minus 1 over K. Okay, so rearrange this equation, you will obtain T0. This one will be P0 is 1400 kilopascal. P, now our corresponding pressure is 1200, and then K minus 1. K for carbon dioxide, you may refer to table. So K for this carbon dioxide equal to 1.289, and then gas constant is 0.1889 kilojoule per kilogram Kelvin. Okay, and then the specific heat constant at constant pressure is 0.846 kilojoule per kilogram Kelvin. Okay, so now K is 1.289 minus 1 divided by 1.289. Okay, so this one T naught over T. Okay, so T now equal to T0 473 divided by this answer, you will get temperature at 1200 kilopascal is now equal to 457 Kelvin. Okay, now we got the temperature. We can find velocity. For example, we can find velocity, because from velocity we can find the density, and then from density we can find the area, okay, and then Mach number. Okay, so now we have the temperature at 1200 kilopascal, temperature that correspond to pressure at 1200 kilopascal. So now from this temperature we can find, first we need to find the velocity. Okay, so how to find the velocity? From this equation, T0, the stagnation, equal to static temperature plus with dynamic temperature, which is V square over 2C Cp. Okay, so now based on this equation we can find velocity. So velocity equal to square root of okay, so substituting all the parameter, okay, to Cp is 0.846, T0 is 473 minus with T 457. Okay, so 0.846 is kilo, it is in kilo, so multiply with 10 power of 3, so you will get the velocity. Okay, so the velocity is equal to 164.5 meter per second. Okay, so there is velocity. So from velocity we can find area. Okay, we can find area, but to find the area, okay, so I will make it here. M dot is given, M dot equal to rho A V, but now rho is still unknown. Okay, to find rho we use equation of state. Okay, P equal to rho R T. Okay, so rho equal to P over R T. Okay, so P equal to 1200 kilopascal. R given, R is 0.1889, also kilopascal, also kilo, and then temperature 457 Kelvin. Okay, so you will get rho equal to 13.9 kilogram per meter cube. Okay, so now you obtain rho. You can find area, which is area equal to m dot divided by rho v. Okay, so m dot 3 kilogram per second, rho is 13.9, and then multiply, v is 164.5, so you will get area is 13.1 centimeter square. Okay, so you get rho, you get area, and then next is you need to find Mach. Mach number. Okay, Mach number equal to ratio of fluid velocity divided by speed of sound. V is known, and this is V, and then C, how to find C? C equal to KRT. V C equal to square root of KRT. Okay, so Mach number equal to V 164.5 meter per second, square root of KRT, K equal to 1.289 for carbon dioxide, ideal gas of carbon dioxide, and then R is 0. This is kilo, so kilo, and then temperature is 457. Okay, so you will get 0.49493, which is the Mach number. But now this is only for pressure at 1200 kilopascal. Okay, so this is only for this pressure. Now the question asks you to find all the properties at along this nozzle, with considered pressure drop 200 kilopascal. Okay, now in that, now it is 1200 kilopascal. You may calculate, you have to calculate pressure for 1000 kilopascal, pressure for 800 kilopascal, pressure for 600 kilopascal, and then pressure for 400 kilopascal, and then last pressure here, which is pressure equal to 200 kilopascal. Mean that you just repeat all this step: find the temperature, find the static temperature, find the velocity, find the rho, find area, and then last you will find the Mach number. Okay, so from this, once you calculate all these properties, you may come out with this table. Okay, so from this table, okay, so you can see 1400, this is a given parameter for 6 velocity equal to 0, rho 15.7, and then C, which is the speed of sound, and then area is unknown, Mach number is 0, and then 1200 kilopascal, which is already calculated. Temperature is 457 Kelvin, velocity is 164.5, and then rho 13.9, speed of sound 3.6 meter per second, area is 13.1, and then Mach number is 0.493. Okay, from this table, basically, as you can see, as we decrease the pressure, okay, so as we decrease the pressure, okay, so as you can see, we decrease the pressure, the area, where is the area? So this area is keep decreasing. Okay, so pressure decrease, area also decrease. Okay, decrease up to this condition 9.63, which is Mach number at the region of Mach number less than 1. Okay, so Mach number less than 1, pressure, when we decrease the pressure, area also decrease. However, beginning from Mach number 1, okay, the pressure, if we still keep decreasing the pressure, okay, still keep decreasing the pressure, the area is now increased. Okay, so the area is now increased, which is beyond Mach number 1, which is Mach number unity. Okay, so at this stage the area is now increased. Okay, increase, for example, at 600 kilopascal, 10 400 is 11.5, and then 200 16.3. Okay, so the area is increased significantly. Okay, so flow area decreases with decreasing pressure down to a critical pressure value. Okay, so this is critical pressure value where the Mach number is unity. Okay, so as you can see, the Mach number is now unity. So at Mach number equal to 1, okay, so the area beginning from decreasing area and then increasing area. So at this Mach number equal to 1, we call at this position, at this location, it is called as a throat. Okay, so it is called so throat is where the Mach number, throat is where the Mach number is unity at the location of smallest flow area. Okay, the smallest flow area, so we call it as a throat. And then interesting is when the area is increased. Okay, when the area is increased, the velocity, as you can see, this velocity is increased significantly. Okay, so even though the area is increased, okay, so area is increased, and then the velocity also increased at Mach number higher than 1. Okay, so this happened due to the decrease, okay, this is happened due to the rapid decrease of density of fluid density. Okay, so and then if we want to sketch the nozzle, so basically the nozzle is decreasing the area and then increase the area. Okay, so this is how the nozzle looks like. Okay, so this nozzle is known as converge. Okay, so first converge and then diverge, converging and diverging nozzle. And then the smallest area here, let's say this is the smallest area, is small. This is known as throat. Okay, so what happened at this condition? Mach number equal to unity. Okay, so I think that's all for this time. Okay, you may read this explanation about the effect of area Mach number after the critical Mach number or critical pressure Mach number. So what happened to the velocity, okay, and then what happened to the density. Okay, and then from based on this example, we will come out with the variation of fluid velocity with flow area, okay, in the next video. Okay, so that's all for this time. See you.